You can see how that spikes at depth when the DBL is present, and then also becomes more elevated when there's no DBL in the surface. Okay, so that's some of our examples of our nutrient data. And then here are just an update of current conditions of salinity. So now I'm showing you two sites, 2565, that's our site in Carrington Bay, and 3510 in Gilbert Bay. Salinity is plotted on the y-axis in grams per liter. And then this is computed using the Great Salt Lake equation of state, where we take a density value and we convert it to a salinity in grams per liter with the equation of state. And this record goes from 2010 to present. So the purple symbols are the 3510 data, triangles are shallow, dots are deep, and then the orange is our site at 2565. And so we can see how, we can see how clearly when there's a deep brine layer, we see a stratification between shallow and deep at both sites, tend to have higher salinities at 2565 at depth, likely due to its proximity to the north arm. In 2015 and 2016, when there was no opening in the railroad causeway, we saw kind of a mixing between the shallow and deep layers, where we no longer had a deep brine layer and the water column was more mixed. We also see an inverse relationship seasonally between salinity and lake level, as you may expect. So higher seasonal concentrations of salinity when lake levels are on the decline or when they're at their minimum. And then in the spring, when we have rises in lake elevation, that's corresponding to a dilution in spring. So if we zoom into kind of what we've been observing recently, we reached a high around 185 grams per liter this fall, when we had a historic low at 4188.5 feet. And then we've seen a continuous dilution of salinity in the south arm since then, which we're happy to see. Our values agree with the UGS values that have been measured, and also with measurements that we've made recently at the new breach, which is another monitoring location. So as of February 7th, we were measuring surface salinities of 165 grams per liter for 3510 and 170 at 2565. So certainly coming down, and we would expect that they're continuing to be diluted. The last thing I wanted to share was just kind of a zoom in on that plot I just shared, just to give you an idea of kind of the seasonal fluctuations that we see in salinity. So if we go back all the way to the October, November of 2021, we were seeing about 168, 163 grams per liter. We had a really poor runoff that year, so we diluted only a little bit to 158 that spring. And then last fall, we had a really poor runoff, and then really lots of lake level decline, lots of evaporation, where we concentrated to about 185, 186. And then since then, like as I mentioned, we've just seen this decline. And thus far, from last November to February 7th, our last measurement, we've seen a decrease at 3510 of 20 grams per liter, and then at 2565, a decline of 16. So really seeing that come down. So now I'll just turn it over to Hannah, and she'll give an update on the nutrient study we're working on.
Hi, this is going to be a really quick update. So these are the objectives of this study: to compute our nutrient loads from inflows in the pools within Great Salt Lake in the South Arm, and to document the impact of the new breach opening. Right now, what has been completed are the load regressions at the inflows and at the causeway breach. These breach loads could be updated as USU is working on a discharge data set at the breach that's going to be a little bit better than the linear regression that we have developed for it. Annual, monthly, and daily loads have been calculated from the inflows as well as the internal nutrient pools. Atmospheric deposition through 2021 has been calculated, and we have gotten a draft outline created. Right now, I'm assuring the quality of the data. I've gone back and looked at some of our nutrient samples from our inflows, and there are some little pieces that need to be looked at a little closer, and also looking at how the breach has impacted that nutrient distribution within the South Arm. The methods and results are being drafted right now. Hope to have a draft of the full report by the end of this month, and then a final report for summer. That's it.
Anybody have any questions for USGS? Specific to next year work. Rather than see how to do stuff. And then you guys will be submitting that your
So my question is, how many would you be limited to a shallow set rather than 50%? Is that complicated? Or it's just what it is? I think it was about 26 years.
Yes, turn it back on. Turn the mic on.
Anybody else have any questions for USGS? All right, so I'm gonna let Jeff, since we made some decisions and there was an executive order, to have USGS provide an update because the berm was put into place, and that was one of the recommendations by the advisory committee. But I also wanted Jeff to kind of summarize what we've done in that committee, as well as where we're going now and how it relates to brine shrimp and maybe where we're going in the end, some of the thresholds that we want to kind of hash out here and maybe provide some recommendations to the Salinity Advisory Committee, although most of us are on that, but it'd be good to get everybody's info on that. So I'm going to Jeff talk about that.
Great, thanks, John. For those of you who aren't familiar with the Salinity Advisory Committee, it was set up by the Division of Forestry, Fire and State Lands and Division of Water Quality under a joint agreement, I believe back in 2017. And they really started to meet in 2019 in force, and really focused on initially what are the gaps in our understanding of how the salinity of the lake changes. And so they accomplished a lot in the first few years. A lot of work was done by all of the different committee members, agencies that are involved. I think one of the key things that came out of that was a salinity matrix that hopefully you've seen. It's been published by the UGS in their library. But what we try to do is try to identify what is the salinity range that is most protective of the beneficial uses of the South Arm. And so on one of the graphs that Christine had showing the salinity, that range that was identified was 120 to 160 grams per liter for the South Arm. And so that's kind of been a mechanism that we've been using to kind of keep an eye on how is salinity in the South Arm changing. And about a little over a year ago, the end of 2021, the committee was concerned with how the salinity concentrations were increasing, and made a recommendation to the state January of 2022 to actually December of 2021 to increase the elevation of the berm at the new bridge on the Union Pacific Causeway. Now there was a berm there. It was there designed to be able to restrict flow from the North Arm flowing into the south. What we wanted to do is we wanted to reduce and potentially even eliminate that north to south flow. And the reason for that is just the north arm is at or near saturation most of the time. And so it's a very highly saline, hypersaline water that would import more salt into the south arm. And so at these low lake levels, that was something we didn't want to see. And so last summer, Forestry, Fire and State Lands was able to get working with the Division of Water Resources and others, was able to get the berm raised to an elevation of 4187. And I think by all measures was successful in doing exactly what we wanted it to do. USGS has been monitoring it very closely, and you can see right when that berm was built last summer where the north to south arm flows were cut off. We were able to still see water flowing to the north arm, which is less saline and could flow over the berm going to the north. Fast forwarding to this last fall, we still saw obviously salinities increasing in the south arm to very high concentrations. And so there was a lot of concern over that and the impact of those high salinity concentrations on the ecology. And so last December, we started talking about, well, what can we do? What can we do about this? And so over the months of December and January, we had a lot of discussions about what we could do. And the resolution, the recommendation from the committee was that we raise the berm to a point where we would basically separate the north arm from the south arm. And the goal really was to be able to build the berm up to an elevation of 4192. So right now the lake is the south arm's at 4190. So we still have about 2 feet of space there to the top of the berm. And the idea was that for spring, well, for the runoff that we're seeing now and through the spring, is that runoff, that fresh water will be contained in the south arm and would really dilute the salt that's in the south arm to hopefully accelerate the decline in salinity in the south arm. And so the berm was built, there was an executive order on February 3rd, and I think the berm was built, plus construction started within a week or so, was completed by mid-February, so very quickly. And so we now have that berm at 4192. And the idea is that, like I said, the goal is to try to reduce the salinity of the south arm this spring and hopefully be able to make enough help for this fall when the lake usually drops down in elevation. So what the committee is working on now, part of the executive order was to develop a berm management plan. And so this is where I think it would be great to get input from this group. Because what we're trying to do is we're trying to identify, well, how can we better manage that berm so we're not doing a kind of last minute, oh my gosh, we got to do something, but we have an actual plan for how we can manipulate that berm to manage salinity in the south arm. And so that's what we're working on now. Just trying to identify, well, what elevations is this, do we want to be thinking about using the berm? And especially what salinities, are there some critical thresholds specifically in the spring that we want to target? Are there some, what is the upper threshold that we want to target in the fall, which is when we usually see the highest salinities? And then what can we do with the berm? I think one of the things that we've been talking about quite a bit is that, dropping the berm when salinities are high in the south arm is probably a good idea regardless, because at low lake levels, because what that does allows us to export salt to the north arm, and when the salinity is highest in the south arm, and then we can rebuild the berm back up to capture the fresh water and dilute the salts. So there's a lot of details there that we're working through, but I think one of the key things that I think is important for the Salinity Advisory Committee is to get input from a group like this, so that as we develop the protocol, we can base it on the best available science, considering all the different beneficial uses of the lake. And And I think my last point is that I think the protocol that the committee is working on right now is really just the start. The intent is that we're going to keep working on the science, we're going to keep monitoring, we're going to keep doing the research that we need to really understand how salinity fluctuates in a lake, how it affects the different uses, the ecology, as well as the mineral extraction industries and other uses, and keep improving on the protocol as we learn. But rather than waiting until we get it all dialed in and get all the science done before we act, the committee felt that we need to do something now, and even as we're continuing to improve the science. So I guess that is my update on the committee. Any questions? I know a number of you on the tag are on the committee as well, so.
Yes, and thanks, Jeff, because I think one of the things that maybe a misconception is, so we picked the 12 to 16%, and I think a lot of people think, well, we just gotta get in there at some point, which is, I don't think is ideal. And so I think that was just a compromise of different interests. What I would ask, because like Jeff says, most of us are on that salinity advisory committee, but I would at least like to get the guy that has done thousands of experiments, based on salinity, phytoplankton, and temperature for the most part, get his kind of take on what the ideal is, and again, timing wise, like you mentioned, spring thresholds and just for areas in terms of brine strength. So
I think the 12 to 16 is the starting point to go. I would say that the key is, one of the keys is in the springtime, that the salinity is low enough that we get a good hatch of the cysts and the acid survive well. I would recommend that I would tend to lean to go a little lower in the spring than 12%, but
does the freshwater streaming help with that?
well, what's going to happen is the freshwater streaming is going to create that lens. And as long as we have that lens, then they're going to hatch, they can hatch and they're going to drop down the higher salinity. But we have to be sure that that lens is formed.
So that bridge that has to be done.
Right. So I would, last year, from what I can see happen, we were saved by that brief period when tackle about 140 parts per thousand in the spring, and we had no hatch until that point. And all of a sudden, boom, it spurred the hatching, and 140 is probably too high for the hatching. Probably need to be able to overcome that in most cases.
Right, it's more about hatching, this isn't super extensive, but.
yeah, so Brad Martin is part of hatching, not very extensive, but what we were seeing hatching system rates all day every 72-hour period. So you can have 40% hatchability at 100 ppt, and going down to around 20-ish at 125, less than 10 at 130, and then really dropping down to close to nothing. I mean, below 2% at 135. Now, again, this isn't very extensive work, but it is indicative, I think, of what Gary is suggesting, that we want to go definitely lower. And I would also opine that, yes, I think these freshwater lenses can truly help on the condition that the cysts get trapped in it. But we also have some cysts that tend to need benthic at certain times of the year, and with much less probability of the cyst ultimately hatching. So, those sort of a couple of comments from my end. I'm really interested, Gary, in understanding, the 12 to 16, we kind of came up with that more than a year ago. I think you'd be doing quite a bit more work on what happens at 15% and even above that
will be nice to have your opinion about where is the optimal and why.
Well, a couple of points. First of all, in the lab, we tend to have cysts at very low salinities, 45, and then transfer to higher salinities for doing the experiments with the nuclei. So that's what I'm basing this on. And we get the best survival usually of shrimp, somewhere between 90 and 120 parts per thousand. So that's 9 to 10, 12%. We get the best survival there. If we push it as we push beyond 120, beyond 12%. Excuse me, I'm thinking parts per thousand, not in percentages. So I'm trying to go back and forth here. When you push beyond 12%, the survivorship goes down and the reproduction goes down. And our experiments that we've recently been doing have 180 or 18%, which we initiated because you asked for us to look at higher salinities given those starting to birth. The survivorship goes way down. Nuclei, some of them do survive and some of them do transition, but the proportion that make is well under 5%. Well under 5%. In fact, I would say it's probably under 1%. And the adults can survive at that higher salinity, but the problem is their reproduction that goes way down. And I mean, when I say way down, we're talking about the reproductive output becomes reduced by well over 95% of what we would see at the 9 to 12% salinities. So the response is quite severe. And so what Thomas is saying is correct. Those cysts, some of the cysts are suspended in the water. They're not going to get trapped in the lens. They're not going to get in the lens. And as a result, you've got to hope, and also you have to hope that there's a large number of cysts and where the inflow is taking place so they do get trapped in the lens. If they're going to go into a part of the lake or move to another part of the lake, our people are going to need it at freshwater lens. So it's getting that salinity down even further is very complicated.
One of the reasons I was asking Gary is, a little over a year ago, before we were hitting these really high salinities, we still had the impression that maybe going up to 18%, might still be acceptable at the time based on available literature. But it seems that that's really not the case for Gary Salt Lake, and appreciate your inputs on
I think, the matrix that the committee came up with, and it's certainly something that we updated as we go, that we learn more. And I know we learned more about brine lines, we learned more about, we're been talking more about the impacts on birds. So Mike, that's something to think about too. But I think as you mentioned is that, even with the brine shrimp is we need to be thinking about what are those key thresholds that are most protected for all of those good reasons.
Larvae and microbialites are really sensitive to this, maybe more sensitive.
And so those are in the matrix, but those are, I know there's ongoing work just trying to understand those.
So Jeff, is there something, that we can provide to the committee, from this work, that will help, to set some of those standards and what would you ask us, I guess, to do?
Well, I think one is reviewing the matrix, make sure we have a pretty extensive library or bibliography there of research that helped us get to where where we are now on the matrix. Yeah, great. And then, I think right now, in terms of trying to have a protocol for the burn is, I think the two biggest questions in my mind, and I'm sure the committee will have others, is, you know, in the spring is when we have all the info. And so is there a number or a range of values for the spring, when we're, in theory, should be hitting our low salinity point that we want to use as a target? And then, because I think the way you kind of envision that is, that's kind of our first measurement point, you know, was raising the burn successful in the first year? And then if it wasn't, now what now should we do? And so then, you know, really our lever we have is to manipulate that burn, raise or lower that burn. But then I think the next measuring point for us is going to be in fall, is when the salinity is usually at its highest point. And that's another measuring point is what we're doing successful on, because then spring number can trigger, you know, what do we do with burn in the late summer period where we can maybe export salts that are environment. And then in the fall, is another point where we can measure gauge success, and then that could trigger raising the burn back up. So those are, at least at this point, I think are the two key points in a year, or, you know, we're just thinking about, oh, what targets should we have in the spring, you know, to be most protective, and then in the fall as well.
Right, well, thanks. My either just total density that we want to look at in fall or as well, so.
This is from Jake Schreiber in the chat. For the purpose of clear, consistent communications and accuracy, I would like to propose that we do not talk about salinity in terms of percentages, rather grams per liter. For example, 160 grams per liter is not equivalent to 16% salinity. The salinity matrix uses units of grams per liter, so it's not easy to use when percentages are important.
Amen.
We always had that problem. Thanks, Jake. Is there any other questions or any comments about that? So what my intent is to have Kyle go through his presentation because it does have some relevance to what we're discussing here and what occurred last year, and then have Gary go through his presentation, and maybe we can talk a little bit more about what this salinity thresholds are and finish up.
Okay. So we're going to cover the brine shrimp demographics. You guys all remember these slides, but hopefully we've got some new changes that I think you guys will like. So let's just jump into it. The old graphs used to have this whole rainbow color of 24 lines of different colored squigglies, and it was just a nightmare to read. We shamelessly stole the idea from USGS and their quartile data for the flowcharts, and we tried to adapt that to our 24-year data set. Beginning from 1999 to 2023. So to jump into these graphs here, the dashed gray line at the top for any given month is going to be the maximum observed in that month in any year from 99 to 2023. The next gray line down, the dotted lines, is the 75th percentile. The next one's the 25th percentile. And then the bottom dashed line that's gray is going to be the minimum observed for any given month. The reason the bars are flat is to show that that value represents the entire month from the 1st of the month to the 28th of the month. because February is weird and only has 28 days, and otherwise it wouldn't parse. So you can kind of get an idea of the scale that that's plotted on. So that is one value for each month. The yellow line is going to represent the previous year. So in this case, 2022. The dark red line is the current year, so 2023. We only have 4 data sets there, January and February, just for our first run. This is going to be plotted on the individual day of individual sample runs. So this is going to be, you can see there's 2 in January, 2 in February. For the yellow line, we have some in June. There were 3 runs. In July, there was none. That's why there's that flat spot going across the top there. The black line running through the center is the average value for the 24-year data set. So where we have data in 2023, that will be included in the black line. Where we do not, it will not be included. Hopefully this kind of clears up. This way we can still represent our 24-year data set, but it's just not as messy. The way this can be used, I guess we do have one more line. So the dashed gold line up here at the top, you'll see from June, July, and August. Due to the low lake levels, we had to pull our boat out of the marina and we weren't able to get out. The co-op was kind enough to share some of their data with us for those 3 sampling periods. So the dashed gold line represents the co-op data. And I'm leaving that separate because we didn't collect it. You guys have 9 different sites from our 15 sites that are currently active or 17 sites in the history. So it's one of those where it's a nice approximation of what we should have got for temperature in July. Had we got out, we would have likely seen something similar. I included the June and the August dates just so you can see that there is some variability between our data set and theirs, but usually we match the overall trend. So that's going to be how the graphs work, month on the bottom, and then the appropriate unit on the y-axis. So in this case, temperature in degrees C. And then I do have the monthly averages on a table on the left side. So currently we've only sampled in January and February. So we take the 2 peaks for January, average those, and we get 2.2 degrees and 1.1 in February. How we'll use this in the future is we can show that January was warmer than the 24-year average, and it was also warmer than last year, 2022. February so far has been colder, and where the red line intersects with the dashed gray line, we can see that this year we set a new minimum for our 24-year data set. So this is the coldest February we've seen since 1999. That'll come into play in the salinity graph, which is next. So looking at water temperature, when we go back and look through 2022, just a brief history because it's been mentioned earlier, we ran into a late hatch, and a lot of that can be attributed to the cold water temperatures through February, March, and April. So there's that component from a temperature side. Otherwise, we've seen 2022 followed the typical trend: cold in the winter months, hot in the summer months. We'll move on from temperature. Salinity. So same style graph. The next 12 graphs are going to have this same kind of outline, same colors. Everything means the same thing. Our salinity is represented in percent because we take that with a hand refractometer at the surface. So that's why we are displaying percent, because we do not do the USGS, UGS adopted protocol that the Salinity Advisory Committee uses for our typical data set. So this is going to be a rough estimate of salinity in a percentage. Again, when we look at the 2023 data set, the red line there, for January and February, we matched the 2022 and actually exceeded it here in February. So again, for the 23 years, February is the highest salinity that we've had to begin a year, which is why we're talking about the burn, because this is all very scary. When we look at the overall average, the dark black line, you can see that we've really hovered around that 12 to 14% for the most part over the last 24 years on average. One of the things that we'd like to look at for 2022, you can see how the gold line really just intersects with that upper dashed gray line. We set new maximums for salinity in every month of 2022. And we're already setting that same trend in 2023. Hopefully with the berm in place, the projected runoff that we're seeing now. It's snowing again today. Awesome. Hopefully this red line will start to dip and we'll actually get below that threshold that we need to hatch the shrimp. So that's how temperature is going to work from now on. Again, we have the monthly averages in the table on the side. So January, we were 16.7% and 17.2 in February. A lot of that's going to be attributed to the big storms that we had, a lot of direct precip on the lake rather than actual inflow and runoff. And
Can you just help me with, so it looks like between February and March, you have a big drop in salinity. I'm assuming from runoff, things like that. Is that enough just from the past data to get us down to a good enough salinity that we'll have to hatch?
okay, let me just make sure I understand your question. So you're pointing out the drop in salinity between February and March as a trend through every line on this graph. And you're wondering if that's going to be enough to trigger the hatch this year. The question is, we hope so, and the berm should help. Everything that we're doing with the berm, because now instead of having a 940 square mile lake, we have roughly half of that. So every bit of inflow that comes into the south arm will stay in the south arm until we reach 4192 and we start to top the berm. So we're getting the best bang for our runoff buck right now with the berm in place. Does that help?
Yes, thank you.
Perfect. I think that covers salinity.
Our calculations show us that if we do reach the 4190, we'll be around 145 grams per liter.
So that was for you guys on the line. That was a comment from Thomas that they're calculating it. When we hit that 4192, we should be around 145 grams per liter. So that's hopefully good. Like hopefully that's good enough with the lens and everything. So fingers crossed this year. All right, our chlorophyll A values for this year. As you can see, we vary widely throughout the year. I follow this typical trend where we typically peak chlorophyll A values in the winter, see a few dips in the spring, usually timed with the hatch, sometimes not. Trend down toward the bottom in the summer months. That June, July, and August is usually bottomed out due to the grazing by the shrimp, and then a rebound through the fall as the shrimp start to die, moving on through winter. So in 2023, this year, we set a new maximum since 1999. I know the overall data set that Gary presents, I think we had higher than 60 micrograms per liter in the mid 90s. That's just not in our database that we maintain. So this year, we're starting off with more chlorophyll in the lake than we have seen in the last 23 years. So there is a benefit there. There should be enough food for anything that does hatch if we can get them to hatch. Compared to last year, the gold line in January, you can see we had one of the worst Januaries on record, and we did actually set that new minimum in 2022. Had a quick rebound in February. We had this precipitous drop off in March, which did not match any hatch that we observed. Not saying it didn't happen, but we didn't see it. I don't believe the co-ops thought at that time either in previous discussions from tags in the past. Then we do see a quick rebound in April and May. Likely that was due to the rains that we got. So we didn't get a ton of runoff through the river system last year. It mostly came as direct precip from storm systems moving in the early springtime. That's where we do see the hatch get triggered, is in that late May, early June timeframe, where the gold line dips off precipitously going into June and bottoms out. Again, we suffer from, we weren't able to get out in July. So I have the co-ops data there, and the gold dash line, where they were showing we're right above the long-term average. And actually, we were above the 75th quartile also. So a missed data point. Hopefully that won't happen this year, but it is what it is. We had to adapt to the conditions that we had. So with everything rebounding in the fall. Like I say, we're starting off better than we were last year. So some good news. We're currently sitting about 67 micrograms per liter in the lake. So that's exciting. Looking at cyst density. So this graph is going to be a little bit different simply because the overall maximum observed is in August is pushing that 800 cysts per liter. That was set in 2021, and it was really due to one site that was 2,700 cysts per liter in one site. So that has an impact on the overall data set because this includes all of our stuff as an average. It's not too much of an outlier because we had a 780 in 2008. So we have seen really, really high cyst counts in August in multiple years across the last 24. Moving into this year for the red line here in January and February, you can see in the graph or in the table on the left, we're sitting right around that 19 and a half, 18. So we pretty much hit that target number of 21 per liter. We're set to be in good condition as far as the harvest model is concerned. We haven't run that yet. I don't have a prediction today, but we can talk about last year's prediction and how that shaped up because we haven't observed the hatch yet. So we may be able to include March cyst counts in our evaluation of that. Key points for this one for cyst density, especially for 2022. While it wasn't the highest observed in June for cyst numbers, we definitely see an increase in cysts in June, and that was fairly early. And when we talk about females producing cysts, we'll show that they just switched right to cyst production early on this year. Key point for August, that August timeframe, we do have that average of about 350, and that comes back into play for our predictive stuff from August for this year. So that's going to be where we are in cysts. Looking at Nauplii, the rest of these graphs are going to be very boring because we have no data for these because so far we haven't observed a hatch, so there are no Nauplii, there won't be any adults, and we can go through these pretty quick. Kind of the same idea. The Nauplii graph starts the trend for 2022 where everything is shifted a little bit late. We didn't pick up a hatch, we didn't detect it until that late May, early June timeframe where they actually really did peak. That could be due to our reduced sampling regime, couldn't get out. We're getting one, maybe two, we're shooting for 2 samples a month. Sometimes we only get 1. So we could have missed some peaks, but I think it speaks to Gary's point of just because they can hatch doesn't mean they'll survive. And that could be what occurred in 2022 in that March, April timeframe. Remember, we had that temperature impact where it was a little cold for them. And then in the salinity, everything was high. 2022 was a stressful year for everyone, Jim especially.
What?
So let's kind of move through these pretty quick. Juvenile density, again, you can see that May, June is when everything picked up. Followed pretty much with the average for most of the year. Maybe a dip out in September, and then kind of an odd bump in both Nauplii and juveniles in November. Moving to male density, followed the similar trend, peaked in June, trailed off. We do see a couple of bumps, like there's at least 3 different generations that occurred in the lake this year, but nothing yet. Female density follows the same pattern. Females with eggs. So a few things here. You can see that egg production also started in May and June. So some of them were happy enough that they were producing eggs at a rate a little higher than the average that we typically see for the year. And then there's this odd bump in November where they switched back to live production. And we think that was due to some of those early storms in the fall and just having the food availability because the chlorophyll had rebounded by that time. So I think they were very confused, and then just having that super stressful year, it was nobody knew what to do, so they just tried something. But that wasn't all the shrimp. So when we look at females with cyst density, you see the same pattern multiple generations, and then you do see that November peak. But the bulk of our cysts were produced in the June timeframe for this year. So,
When you have that up, may I ask a question, thinking about the patch for this year?
Mhm.
Because of the mistiming, and you can repeat the question, but because of the mistiming of the cysting that happened last summer, so when they had cysts, probably because of salt stress, and then those cysts were kind of leaving dormancy in the fall as they had their second batch of cysts. Do we expect less hatchable cysts this spring?
okay, so to repeat that, so one of the things that we saw last year in 2022 is with this early cyst production, the dormancy was very weak this year, and we did see quality issues with that dormancy, and we expect that a lot of them broke dormancy and hatched in August with the freshwater direct precip that we got from some big springs at that time. And the question is that going to lead to lower hatchability this year? And I think it could. I think one of the issues that we are seeing is already our decapsulation rates are lower. So typically in the fall, we count anywhere between 80 and 90% decapsulation rates. So that's going to be 90% of the cysts that we count have embryos in them. We're seeing numbers on average in the 70s and some as low as 50%. So yes, I think that's going to be an impact of the 19, the 20 cysts per liter that are out there. We are pushing closer to that. Probably 10 of them are going to be available to hatch, and the overwinter cyst survival is going to be, I'm guessing lower than on average, but the literature does cover anywhere from 10 to 90%. I think we're going to be in that below 50% for overwinter cyst survival, which is why the 21 is the 21 and not the 3.5 that we actually think we need. So that's where we are there. Okay. Cyst. Okay. Total adults follows the same example here, just seeing that 3 generations, June, August, and then November. And now we'll get back into the harvest prediction. So if you guys remember in the August tag, we predicted where we were going to be based on the cysts left in the spring of 2022. So this is a slide directly from the August tag. So this is the 2022 forecast. This is the forecast model with the upper arm that is density independent, the downward curving arm, which is density dependent, and then that red circle kind of delineates where we should have fallen on that curve. So spring counts were as low as 15.9 and as high as 54.39. That's being driven by some outlying sites. And that translates to that 54.3 in the spring translates to 56.6 in the fall. The 15.91 translates to the 101 in the fall. And that's going to be an average of, we should have expected somewhere about 103 cysts per liter. What we saw in August was 348.9 cysts per liter. So pushing 350 cysts per liter, it's quite high. One of the issues with outlying data, one of the things that we have done when we report this to our website and to the industry is anything over 30% of the mean, we treat as an outlier. The way the model was built by Gary, a more reliable sense of that is using anything above 2 standard deviations. So anything 2 standard deviations above the mean is treated as an outlier, gets dropped from the data set, and then gets refigured. September, we had 221 cysts per liter. And that'll come into play when we look at dropping out those outlying sites. So this next slide, this is the same information, but with those high sites dropped out. So you'll see that we had in the springtime on the upward curve, we're 15.91 because that's set, but that 56 drops to a 34. And that 34 now translates to 114 on the 18. So it's going to put us, you saw that red circle kind of tightened up right around the peak of the curve. That peak of the curve, since that was fixed, we haven't seen anything over about 200, short of 200 cysts per liter until this year. Again, when you drop out that high site in August, it takes that 340 down to a 191, which removes August as the highest site. And we can rely on that September data of 221 per liter because there were no outliers through those two samplings. So this year we should have expected, based on our numbers in the spring from 2022, to be right at the maximum of the cyst production model. And I think we hit it. So even in this really stressful year, the model holds up. And that is actually my last slide. So if anybody has any questions, I'd be happy to take those.
The model should be not, well, we're in a world that the model was not built.
Yes.
And what we know from the high salinity studies in the laboratory that we've done now, and you got it in your data there, this we built in, the model built in a period where the live young meat produced rather than cysts. And what happened under this year is novel. Outlier report basically that live young production went way down and cyst production went way up. If you think about it, mom and dad, if I produce live young that are going to just die because the salinity is so high, produce the cysts that are diet causing, right? And hopefully next year is better.
Yeah.
So this is built on the pretext. The model was built in years where we had this high live young production, and under this high salinity now, that high live young production has gone way down, and the cyst production has gone way up.
The other thing we saw, Kyle, that was interesting is that up to 2 years ago, in the fall around September, we typically see about 90 to 95% of the cysts being in diapause, only about 5 to 10% quiescent. The last 2 years, we saw as high as 50% of the cysts being quiescent in the fall. So a very different, sort of dormancy pattern. The other thing we're finding, just looking into it, is, we kind of refer to it as recalcitrant dormancy or diapause, where the diapausing cysts are actually stronger diapause. It takes more manipulation in order to pull them out of that diapause period into quiescence. So definitely different patterns that we're starting to see that might be interesting to look into.
So that may be a better answer to Lonnie's question. They could be any stronger frequency too. So.
I have a Phil question. Phil, this is a little off topic, but with that spring peak of chlorophyll, can you remind me who's in that peak? Is it at what percent is the Malleola, or what's the abundance of the other species?
Are we talking about spring of 22 or 23?
There always is a little peak, right?
Yeah.
But if it's different this past year.
Yeah.
Okay, but he's got work moving.
Yeah, given the alternate reality fiber lens and assessments, we measure it 2 ways. We have a laboratory that will integrate additional microscopy so you get the species, characteristics, your custom seeing, and then try DNA that barcoding, which takes all of the fiber length and it searches for certain DNA sequence. And each species in a library is supposed to be tied to a sequence, and it'll tell you what's in that sample, and it changes the relative abundance. What you can't do is compare the relative abundance in the barcoding to microscopy. Some taxa amplified sort of a PCR process. but you can still track kittings at a time. And so microscopy data, it's very much dominated, as far as count and biomass, which is probably something Gary agree with and for a while. The barcoding patterns have changed a bit. So in the spring of 2022, we didn't see major composition shifts, anything too good from prior years. We didn't see a seasonal oscillation between two dominant DNA sequences that occur, which is one that is more prominent in summer, another is more prominent in winter, and they apparently look very similar at microscope as well. Viridis from scope data.
There's subspecies, right?
It may be. It's hard because the taxonomic libraries sequence aren't differentiate subspecies. So you can tell with two different sequences what exactly that equates to under a microscope doesn't matter. So you get a little bit of a seasonal pattern there, but nothing that seems too out of ordinary in the past several years of looking at this. One thing we did notice was that in the summer and fall, we started seeing more sequences, So,
And we saw that in the field as well.
okay, yeah, it's nice confirmation there, where during the highest salinity period in summer and fall, they start showing up. They've been just about non-existent prior years, and then as they start declining, as we go up winter, but those drop off in the latest zones.
We've also seen peaks in Halo-Archaea in the South Arc, which we haven't seen.
Yeah, I mean, that was in summer, fall.
Fall.
Okay, yeah, okay, interesting. Yeah, but there's been a few other shifts, axis and diatomics dropping out. There's some of these waters to work, but there's patterns that seem to correlate with the brightness of these said last year.
So Salina is that orange alga that we usually see in the northern arm, and the Halo-Archaea makes the water pink in the northern arm. So we're starting to see those species in the south arm as the salinity goes up, which is what you would predict.
Yeah. Any other questions for Kyle about the demographics? Right, we'll shift to the last presentation of Gary.
Okay, if you want to clear it, say
Does that work?
Yep, there you go.
Okay, thanks. Okay, a couple of, okay, a couple of things I want to cover today. First of all, we have a manuscript done on feeding selectivity by the brine shrimp on different phytoplankton. This was already built into the Great Salt Lake ecosystem model that I've been presenting to you tag meeting after tag meeting, but we've got the manuscript done. The important thing to point out here is that brine shrimp are selective in their feeding. The earliest studies back in the 1960s done with Great Salt Lake brine shrimp were done with phytoplankton that were not from the Great Salt Lake. They used Dinelliella from an ocean sample. Whether that was our Dinelliella or not, I don't know, but they used species of phytoplankton that the brine shrimp would have never been exposed to. The species we're using here are Dinelliella viridis, Euhalothaceae as a cyanobacteria, and Nitsia as a diatom, a bacillariophyte. And we can see from the lab experiments that we've done that their brine shrimp preference in their feeding is correlated with how well they survive in that type of phytoplankton. It's what you'd expect. You eat the stuff that you do best on. And there's a shift, especially among the adults, where the adults shift from their second most preferred food for juveniles and nauplii being Euhalothaceae, the cyanobacteria, The adults have a second preferred food, which is the diatom. Now, this manuscript is all done except for one thing. We're trying to see whether that shift might be related to stoichiometry of the phytoplankton. So we're looking at carbon, nitrogen, phosphorus ratios. And I suspect that the adults are shifting to a their second preferred food being the diatom because it's higher in phosphorus and you need the phosphorus for reproduction. That's what we're hypothesizing, and we're in the midst right now trying to get the phosphorus data. Hopefully, knock on wood, this week we'll have the phosphorus data. Okay, phytoplankton this last year. From our counts, you can see on the over there on the far side that phytoplankton tended to be, I have to look at this, it's hard to do. Phytoplankton, when we look at this here, you can see that in the blue line, which is this here, has generally been higher than in the past from 5 years, 2017 to 2021. Now, largely that's probably due to lower shrimp numbers raising it down. This is the salinity conditions this last year. And because it was not raised down as low as on average throughout the year, in the fall, it recovered very rapidly. And as Kyle pointed out, as of February, we're already up here at a higher point than we haven't seen in a long time. I'll go at something like 65, 67, something like that. Micrograms per liter. In terms of composition, there's no really big changes that we can see over the entire year. But one thing that we did see was in the highest salinity period, we tended to get some peaks in the diatoms and peaks in the cyanophytes, the blue-green algae sarcomony, cyanobacteria. I know, thanks. But I think my idea of why that is the case, we have higher peaks in terms of the abundance of cyanophytes and the slurry diatoms is my hypothesis is that they were knocked off with the microbialites and they got into the water column. Because they shouldn't be growing at that time of the year. At that high salinity, they shouldn't be moving up. And at that time of the year with the temperature, they shouldn't be moving up. But what's happening, I think, is that microbialites are stressed and they were released off there, just like the brine fiber, they were released into the water column. And as a result, you've got more of this water column than you normally would have. Okay, the main thing I want to focus on today is the Great Salt Lake model for nitrogen built into our ecosystem model. And it's built into the abiotic module of the Great Salt Lake model. From past meetings, you see where I did quick back of the envelope calculations of where nitrogen was going in pools in the lake. This model now takes into account fluxes within the lake provided by different factors like dying phytoplankton, brine shrimp bodies, brine shrimp fecal pellets, how quickly they decompose, and where that nitrogen ends up. So here's the first draft of the model that's coming up. Phytoplankton up here, this column here of the model is the upper layer and the deep brine layer of nitrogen fluxes. These are the changes that are taking place in nitrogen, inorganic nitrogen in the water on a weekly basis being calculated. This model works running on a weekly basis. So these are the fluxes. This row here is phytoplankton. This is shrimp bodies, and this is shrimp fecal pellets. The phytoplankton have a single path That's because they decompose so fast and release their nitrogen so quickly that it never gets down to the deep brine layer. It's all in the upper layer. However, the shrimp bodies don't decompose as quickly, and they're sinking. And some of that nitrogen gets down into the deep brine layer, and some of it is in the upper layer within the lake. Same thing for the feces. Some of it decomposes in the upper layer, majority of it decomposes in the deep brine layer. And let's go over here to this column. This is biotic pools. This is how much. This is one battery say. Oh, well. Sorry on them, folks.
Maybe we can have a little discussion about it. Of the, what do you call it? I'm trying to remember the order. The crococalis, which the Fanaphysi and Big are both in.
Yeah.
And they're very related and they look the same under the microscope. Do you know that what you have in your feeding experiments is Fanaphysi?
Yes.
Could it be both things?
It's we have a thing,
Okay.
but we have an electric.
Yeah.
We have
I
barcode we tested.
I thought you did. I thought you could. I didn't
We're
remember.
the same thing with the diagram we give it to you.
Yeah.
We have barcode.
Yeah. Because the Fanaphysi we're seeing in the water column around the turbulates, but we're only finding big VC in the maps. So in the
Yeah.
planktonic,
Makes sense.
in the planktonic compartment, we're seeing that's always minus.
Oh, well. Technology.
Yeah, can I take this opportunity to introduce Tyler? Tyler Mifflin is with SK Films. He's a Canadian, but don't hold that against him. And he is very friendly, does a lot. But he is working on IMAX films. Some of you may be familiar with the current film at Clark Planetarium, Wings Over Water. And if you haven't seen it, you should. I just sent my students to see it, by the way, and paid for their admission. So I think it's really, he has an IMAX Great Celebrating project that's happening right now, a film that would be shown in the West in natural history museums and planetariums. And I asked him to come to this meeting so that he could meet lots of you, so maybe during lunch, particularly Alabama Beach. She's close. Anyway, so just so you know who he is, you could talk to him during lunch. Great. Okay, go ahead.
Okay, Mary. So this, I pointed out this column is fluxes in the lake. This column here is the pools, what's being stored in the phytoplankton, what's being stored in shrimp. And then in the middle here, we have a purple column, which is what you would measure in the water. Okay. And then the graphical output. Now let me point out this preliminary model. And this is where I was talking to you about the phytoplankton and the shrimp in the Great Salt Lake model over a year ago. But let's look at what it tells us. And like, it's exciting what it tells us, but I'm still not sure that it's all correct yet. All right, first of all, we have to be concerned with decomposition of the nitrogen sources. And I showed this to you in past CAD meetings, where this is the rate at which the phytoplankton decomposes at different temperatures and salinities of water. This is decomposition of the shrimp bodies at different temperatures and salinities. And as of now, we have pellets only at one temperature, one salinity. We have 4 going on right now, experiments with this. So how do we put this into the nitrogen model? So I took 2000 to 2020 2020, a period in which I talked to you before on how this phytoplankton and shrimp were changing in the ecosystem model. And I took those salinity and temperature conditions and calculated for a year on a weekly basis that this is the phytoplankton. You can see it decomposes at a higher percentage per week. The shrimp bodies are decomposing in the blue line here at a much slower rate per week. And the fecal pellets at an even a slower rate per week. And that's put in there by scaling it to the temperature and salinity responses for the body. Just took the 20 degrees centigrade, 120 ppT salinity, which we have for the bodies as well, and then scaled it up and down relative to how the plants were decomposing. So that tells us what we would expect to see on a weekly basis with decomposition. Now, where does this decomposition take place? This upper table here I presented to you in a past tag meeting, and I was teased earlier about this, and I said that the shrimp fecal pellets were like little rocks because they're falling straight down to the water column. And almost all of that decomposition of shrimp pellets you can see 24% of what's in the that is going down into the deep brine layer. 76% is hitting the bottom in a place where there is no deep brine. In other words, it's on the benthos on the bottom, but it's not on the deep brine layer. Shrimp bodies are falling 80% of the decomposition is taking place within the water, 20% is in the deep brine layer. And all of the phytoplankton is occurring in decomposition, is occurring in that upper layer. It's so fast. It's all so slow. This is basically on the 2015-2020 conditions of temperature and salinity. All right, now this is a big unknown. How much does the deep brine layer nitrogen turn over between down deep and upper layers? And to get at this, what I did was I took the concentration of inorganic nitrogen in the upper layer versus the deep brine layer, and looked to see if that deep brine layer was increasing or decreasing, whether that upper layer was decreasing or decreasing. And as we know, we published this, the original USGS paper, Dave Nass's paper, and the work that the GSLEP published before that, Dave co-authored from that, shows that this nitrogen could accumulate in the deep brine layer, and it didn't necessarily turn over and go back into the upper layer. And so at salinities below about 140 ppT, there's no turnover. What happens is stuff falls into the deep brine layer and it sits there. Above about 170 ppT, there's complete turnover. And if you look at values changes in the nitrogen from the deep brine layer and then seeing it go down and increase in the upper brine layer, the upper level of the layer, there's a range in which there is some turnover. It's not complete and it's not zero. That occurs between 140 and 170. And if you plot out how much of a change there has been in the deep brine layer, that gives you the turnover that occurs within that region, and that's this line 7, that's the lines here. Taking that value, putting in the salinity from 2015 to 2020 was each month of the year. You can see that for a good part of the year was that period, 2015 to 2020. There was no turnover. But then we get into the summer months and into the fall, when salinity goes up in the day. And we see that there is some turnover that takes place. The highest was in October, with about a 16% turnover per year. Now that would be if you had that level for the entire year. averaging over the entire year is about 5% is all turned over between 2015 and 2020. Only about 5% of the nitrogen was being released from the deep brine layer back into the upper layer. Okay, so what does this all mean? Run the model, what does it tell you? Well, it's running through the braids, through the brine shrimp phytoplankton inside of the model. And in the upper layers of the lake, the model predicts 0.93 milligrams. That's the stage here, that's what happens when you've been doing phytoplankton graphs with micrograms, then you get to nitrogen, and now the unit changes to milligrams. Stayed in micrograms. Gets up to 0.93 milligrams per liter, what the model predicts. What was observed from measuring peak inorganic nitrogen in the lake for those years? 0.95. Pretty good. Like I said, this is early on, don't take it to the bank here. Deep brine layer in 1 year should be at 1.23, no, 1.25 milligrams per liter. You can't test that number directly because what was going on in those years was accumulation in the deep brine layer. So how did I test the model's running here? Is that there's nothing in the deep brine layer already, and you're just adding to it for 1 year. So what I did was, I went in 1995 and 1996 nitrogen data in the water. And those years were a point where we basically went from the deep brine layer increasing in nitrogen abundance and then starting to decrease it. And I asked how much would it, went from a decrease to starting to increase. I asked how much would it increase in a 1 year period, and it increased by 1.23 milligrams per liter. So we're in the ballpark. Where we see nitrogen in the upper layer is phytoplankton at about 30%. Shrimp is providing about 60%, and the shrimp fecal pelt is providing, let's say, about 10% of the nitrogen. If we look at the deep brine layer, phytoplankton increases nothing. Bodies in the shrimp at about 85%, and fecal pelts are providing about 15%. So the shrimp are the ones that are largely producing the deep brine layer nitrogen. They're sinking down to the bottom, phytoplankton could not do. Now, once the milligrams of nitrogen per liter in the upper layer, the dark black line here is what is observed by months from sampling in the lake. The red line is what the model produces. It's given the right pattern. It's overestimating how much should be measured in the lake on average. But remember, it has not taken into account birds removing nitrogen, hasn't taken into account any of the microbial like brine frost yet. Locking on. So that's going to take the red line and move it down. And that's included in the model. So check with facts that come out of the model. So phytoplankton cellular physiology. I never thought I'd be reading papers on phytoplankton cellular physiology. But with the model, when I first ran the model, there was a problem. You would expect that the phytoplankton, when they're out there by themselves and not being grazed upon, should be reducing nitrogen to essentially zero. You see that all? And they're not. Based upon what is in the mass of phytoplankton out there and the nitrogen content of the body's phytoplankton. Well, I looked at the physiology data, and on a weekly basis, Phytoplankton are using 28 to 36 times their cell nitrogen content in just cycling it through their bodies. That had to be built into the model. It's not just what mass of phytoplankton is out there times the nitrogen content, but it also has to take into account the cycling. Cycling is the phytoplankton are excreting. The phytoplankton are dying and being replaced. That has to be taken into account. Brine through pellet deposition. 1,500 pellets per centimeter squared per year. That's too high. I think it's probably going to be more like 1,000. But that's a huge amount being deposited on the bottom of the lake. As Christine told me, traps get filled up real fast. That's what's going on there.
It also matches with the fact that we find intestinal microbes of the shrimp inside fluids.
That's right. They're making the saints. Okay, the problem we have is that the Great Salt Lake upper and deep nitrogen measures are really insufficient for testing them on a detailed basis. And I'm hoping you guys get through the data and looking at it. So many of the samples that are on your the web page already, either there's no MH4, no ammonia reported, or everything is reported as low sensitivity to be measured. That doesn't help in this sort of trying to test the model versus what's going on. And to be honest, we have too few samples per month and year to be able to look at the models, predictions, and detailed testing. Where are we at with the model? Well, we haven't finished the fecal pellet decomposition studies and the safety studies of those pellets. And we're testing how fast they rot the different facilities. And we're just about done with that. It makes no difference. They drop so fast that no matter what facilities you're looking, they're down on the bottom within a day. We need to have studies on avian excrement and feather decomposition effects, which would be really important to the lake. And I would imagine that avian excrement is going to be like phytoplankton. It's going to go straight into the water in the upper layer. It's not going to be down the deep brine layer. We need to build and incorporate that deep brine layer, the upper level volume relationship. The model right now has that as a single value. It needs to be dynamic. So as lake level drops, the deep brine layer amount becomes smaller. So it's really similar and it's going to turn over. So that needs to be made dynamic, working with that right now. And that is going to be functionally with the bathymetric models, maps of the lake. The model parameters need to be defined. These were first shots built into the model. And then one of the real hard parts is going to be incorporating that nitrogen model into the ecosystem model as a whole. The way it's running right now is the ecosystem model is running for the shrimp and the phytoplankton, and it's feeding those values back into the nitrogen values. So the model, the nitrogen model now is not feeding into the amount of nitrogen that the shrimp and growing under. They're just giving the bodies and the consumption back to look at nitrogen flow. The reason why this is so difficult is because the ecosystem model works over 5-year projection models every year for 5 years. Well, think of the deep brine layer. You've got to put in now a confident value for what nitrogen is going to be running there as a starting input. And we may not have that always. And then for the next 5 years, that deep brine layer is either increasing or decreasing depending on how much turnover takes place. And so making this linkage so that the model feeds in nitrogen, and then the next year that nitrogen that you calculated from the previous year is used to get the phytoplankton and the shrimp to grow, which then gives you a new nitrogen value, which determines the next year's shrimp and phytoplankton growth. It's not easy to do at this stage. This is going to be a real time-consuming effort to get that to work. And that's what I have to say.
It seems to me that you might. Seems, Gary, that you might have to add bird management to the model in terms of how it affects the brine layer.
Eventually,
What?
burn man.
Oh,
It's obviously you have to take. No, the burn, he said burn. You're correct. Eventually, that's going to have to be done. But at this stage, I'm trying to do it based on past date when there wasn't a burn. Because that's what we have to build the one testimony.
Okay, so I apologize, this is a really, because most of the fresh water that comes in to the lake is kind of separated from the lake right now, right? So how are you using the nitrogen that's coming in from those freshwater inputs in this, and it is right now is potentially being taken up by vegetation? He's not understood.
Based on a lot of past calculations, what it looks like the lake is going on the short term. Based on the short term, is that what is coming in is the nitrogen wise is very small compared to the pool that's already. Okay, so for the short term, those inflows are being considered, are not being considered. Over a long term, so if you increase lots of nitrogen coming into the lake, decrease the nitrogen, there will be an impact, but in the time frame that I'm looking at right now, that's too small an amount to be worried about.
As well as with the mineral content.
Yeah.
I have a question for Andy and Chad. Would it be important to include an atmospheric nitrogen deposition based on like a nitrogen model with respect to particular inputs from adjustments?
Again, it's like the freshwater inputs. On the short term, the shorter time span that I'm looking at right now, the answer is probably not. But if you looked at it over a longer, multi-decade type of approach, probably yes. The same thing with freshwater inputs.
Why do I feel that it's really curve mentioned in excrement would remain high? The other private. I was expecting it not to be that.
My suspicion is that it dissolves pretty much into the water, and therefore it's not going to fall straight down and it's asking for it before it breaks down. And if you think about the excrement, it's going to be high in nitrogen to begin with. And so it's going to go into the water out very quickly. And I imagine it decomposes fast too. Feathers probably not.
They don't like to see it.
Well, it's a real now, but I looked at, there have been some studies done on decomposition of bird feathers, chicken feathers, soaked in water and how fast they decompose, and it's about 13%. I want to say for most is the figure that people have published. I'm looking at some strengths. It's not the normal stuff that I go looking for, right? You know, you look at the nitrogen fluxes in a phytoplankton. You know, you sit on the internet, you go through this stuff, and then all of a sudden they go, somebody measured something somewhere, and you get these types of figures.
Anybody else have questions for anybody? All right, well.
Okay, so, this is kind of a 35,000 foot level question. But I've been tracking, legislation during this session. And it seems like legislators are hesitant to think about an elevation range. And they're more focused on salinity concentrations, and that's fine, because they're related. And how do we translate what we're talking about here into action to bring inflows into the lake through legislative support? And I just think that there's this key disconnect in a legislator's mind to understand how elevation does affect salinity concentration in an elementary way. And how are we going to translate what we're talking about here into bringing water into the system with a commitment? And that's what I'm trying to figure out. I refer to Great Salinity Elevation Matrix often. And there's a data line in the matrix for the south arm of salinity concentrations as you have elevation ranges. So I'm trying to draw more attention to looking at that and making that relationship. The legislators to recognize that, okay, so if you look at this range, this is where salinity concentrations can be affected. And I guess I just need your help in how to simplify that even further so we can translate talk into action. There you go.
So that's an easy question. Yeah, I mean, well, one, when you talk about legislators, and Tim was the legislator, I like to call him how he always answered those questions, because we legislators are particularly don't watch, but that, I don't think it is, one of the things about this system, I think we all know is, it's complicated. There is no like one number, one thing to focus on. It's not just salinity, it's not just nutrients, it's not just the vitamin, it's not everything contributes to it. And so you can't just pick a thing and then try to get that, because part of the reason that this is so productive is because it's dynamic. So you have less water, some years that's good. You have more water, some years that's good. There's no real thing that you're shooting for, because I don't always mention that as you have the elevation changes, you expose more opportunity to different species or different groups. That's just the nature of the system. So because the change is good. So as long as we can maintain the change in a frame that is probably a little higher, but I don't think there's any particular
for anything.
I don't know if anybody else has a take on that. It's just, I think the system, I know when the decision was made as far as the urban modification, that was based on just the best information that we had at the time, you know, and I want to mention this too, because I thought of it when Jeff said, you know, this advisory committee was put together in 2017. And I'll be honest with you, I thought, well, what are you gonna do? I mean, measure the salinity. Is that what we're gonna do with this whole committee? But the thing is that there wasn't the foresight to put that together, that group together, and actually the work that's been done in the last 6 years or so, there would be some opportunities missed in that problem. The fact that a lot of this research is being done well in advance of the problem, that you could be a lot of our proactive rather than reactive. I think that something, you know, just putting that group together probably saved life this year, in my opinion, because we could have been sitting here and let fresh water flow into the North Arm and not taking advantage of it, and instead it ran left already, but I can certainly say that he for us probably had to jump through a lot of hoops to get that executive order or provide the information for that, because I'm certain that a lot of the legislators or policymakers depended on the experts. These groups are a compilation of all the experts, so that's a great thing. Yeah.
I think what you said, John, is really insightful because it is a complex system. There's little parts that we don't understand. We keep talking about the groundwater, for example, and the salinity advisory committee, and not understanding like what the water is moving through and where salt is coming from. Christine's nodding her head, fishing is better than anybody. But I think Lynn's question about the legislature. Many of us have had to spend a lot of time with media recently or legislators, and when you're speaking to people who aren't familiar with the space of science, those simple messages are really important. And if we had an elevation number or a percent of salinity that people understand, if we have that at our fingertips, it really, we need that kind of bullet point messaging for those groups. And that's not what we need to do here. You know, we need to set up. But to Lynn's point, we've got to have some kind of guided numbers that we can just say, because I guarantee you they're not going to have this level of discussion in the legislature. Anyway.
I think that the management burden helps us manage salinity, regardless of the volume. You know, it's not on and off, it doesn't happen quickly, but it allows us to do it. But I think the message here is that that's ultimately a temporary measure. Because if you look back 5 years, 10 years, 20 years, we've had some good inflows occasionally. But if you look at the averages, they've been quite similar during that 20 years of drought. And if you take those average inflows, the lake will continue to go down and will ultimately end up disappearing, and we will create huge dust storms. And I think that's the simple message in my mind.
Thank you.
Yeah, I agree. It is temporary. The trend is not good. We've been maybe like decent water users. One thing I wanted to do is maybe I can take the information that Gary has as far as salinity thresholds for the brine shrimp. And give that to you, Jeff. That way, at least in the salinity advisory committee, we can discuss that and based on data that we have available. So, does that make sense? Yeah, okay. Anything else that anybody wants to mention before we close this meeting? Yeah. Do that, so.
Yeah, the Wallace Center is focusing their symposium this month on saving graceful lake. I forget what the exact title of this, but it's March 16th to 17th, I think. And they're inviting registration. You can register and attend remotely or in person. Many of us will be a part of the program, and it's really great because the State Symposium brings a lot of focus to whatever issues they select for their programs. So it's really an honor to have Great Salt Lake. It's no surprise, but it's an honor to have Great Salt Lake this year program focus.
And it's available online, virtual. Yes. I can send it out to everybody who's there.
Great. Awesome. Well, thanks. And then let's go ahead and set the next couple of meetings just so it's on count.